Hi guys, it's Mrs. Millison. All right, we're going to tackle our last topic for this chapter, and that is conditional probability. But the good thing is you've seen it before, okay? First, let me bring out my little cheat sheet for the whole chapter. So conditional probability is down here, and we're going to talk about what this formula means. But you'll notice that conditional probability also exists up here, okay? So you can use conditional probability to calculate the and of dependent events. Okay, so we're going to do a little bit of everything. All right. Now, first of all, where have you seen conditional probability before? You've seen it in chapter 1 with conditional distributions. Okay, we have a table here, a two-way table. We asked 200 students their favorite snack and their favorite color. So we categorize them by snacks and colors. Okay, so in chapter 1, our conditional distributions were simply a cell in the guts over one of the margin totals, okay, because these were the conditions. So we said, what percent of chocolate lovers like the color blue? So the chocolate lover is the condition, okay? So what percent of chocolate lovers? Well, 59 people like chocolate. And of those, who likes the color blue? That would be 36. Okay, so that's how we did, what is that, 0.61? That's how we did conditional distributions in chapter 1. Matter of fact, we did the conditional distributions of everything against its total to figure out if there was a relationship between the two variables, okay? But with probability, we're going to pull out a specific conditional distribution. Okay, and how it appears in probability, I'm going to write the formula up here. The probability that event A occurs given that event B occurred. So this is the probability you're finding. This is the condition, okay, or the event that has already happened. So what this is saying is this probability of this event A is going to be somehow influenced by the event B happening, okay? And the formula we use to find that is the probability of A and B, all divided by the probability of the condition. So it's always and over condition, okay? And if we think about that, I've turned this sentence into a conditional probability statement. So this is the probability that somebody likes blue given that they like chocolate. Let me put that down. This bar up here is the word given. You might not see the word given in the problem though, so don't just be looking for that word. So if I follow this formula, I'm going to need to find the probability of blue and chocolate. So the color blue and the number, and chocolate is 36 over 200 divided by the probability of chocolate, which is 59 over 200. And of course, when you divide by a fraction, you multiply by the reciprocal, and 200s cancel, and we also get 36 out of 59. Okay, so these are the exact same thing. They're just worded a little differently. This is more about distributions, and this is more about probability. Okay, so it doesn't matter what your thought process is, especially from a table. Okay. Whether you just want to think about these as a conditional distribution or as a full-on probability, it doesn't matter. I'm going to go back and forth on what process I'm going to use. Okay, so for this one, we want to know the probability that a randomly selected person likes the color green given that they like candy. Well, I'm just going to do it through my conditional distribution. So I know this means of all the people that like candy, 66, there are 28 that like the color green. Okay, so 28 out of 66 is 0.42. Okay, so again, I don't necessarily have to go through this because I already am. That is the and. That is green and candy. Green and candy. This is candy. Okay, 66. So it's all the same thing. All right, let's do the probability that somebody likes the color red given that they like chips. And I'm going to do it by conditional probability. So I have to do the probability of red and chips over the probability of chips. So red And chips is 15 out of 200. And the probability that somebody likes chips is 75 out of 200. Okay, so of course that is going to simplify to 15/75, which is 0.2. Okay, all right, we'll do the next one as a conditional distribution. What's the probability somebody likes chocolate given that they like the color blue? So I'm going to look at this and I'm going to say of all the people that like the color blue, so there's 60 of them, how many like chocolate? 36. Okay. So again, same thing as this, because chocolate and blue is 36 out of 200, and blue is just 60 out of 200. Okay. All right, let's do two more. No, I can't see the table anymore. Probability somebody likes candy, given that they like the color red. So we'll do probability of candy and red over the probability of they like the color red. Okay, so let's find candy and red. Candy and red is 20 out of 200. Okay, 20 out of 200. Over the probability somebody likes red, so that's 40 over 200. That ends up being 20 over 40. That's easy. Okay, there's a probability of 0.5. Okay, last one. Probability someone likes chips, given that they like the color green. Okay, so again, I'm going to do it just as a distribution, conditional distribution. So of all my people that like the color green, that's 50. How many like chips? 12. So 12 out of 50 is 0.24. And again, these are all the same thing, okay? So you're very familiar with conditional probabilities with a table. Okay. All right, so that's the first part of conditional probability. Now let's look at it in terms of trees, okay? Okay, we're going to look at a tree for dependent events, because my example I just showed you with the table emphasized that, but now I want to show you where this comes from, okay? And this is best seen, most easily seen on a tree, okay, where we have dependent events. So our dependent events are going to be, we got a bag of 10 marbles, okay, so there's 10 marbles total. And you're going to pick 2, okay? So we're going to do this as a tree because this is a sequence of events. Without replacement means once we pull the marble out, we're not putting it back. Okay, so we're going to start with our 10 marbles. The first pick is either going to be red, green, or blue. Okay, and we know the probability of getting a red marble is 3 out of 10. Green is 5 out of 10, and blue is 10 out of 10. Oh, 2 out of 10, excuse me. Okay, so this was the first event. First event, probability of the first event. So there's your first marble. Then we're going to pick a second marble. And depending on what color the first marble was, our probabilities are going to change for the second color. Okay, our options are still red, green, and blue. Now, let's do our probabilities. Now, this is without replacement. So once I pick this first marble, I don't put it back. So I don't have 10 marbles anymore. I now have 9 marbles. So all of these probabilities should be out of 9. Okay? So if I've already picked 1 red marble, I only have 2 reds. So I have 2 out of 9 chance of getting a second red. I haven't gotten any greens, so I still have all 5 greens, but again, only 9 marbles. And I haven't picked any blues, so I still have all 2 blues. Okay? But again, out of 9 marbles. Off of the green, I still have all my red, but I've got 1 less marble. I've got 1 less green and 1 less marble. So this is 4 out of 9. I still have the blues, but 1 less marble. Okay, if my first marble was a blue, second one was a red, I still have all my reds, but 1 less marble. Still have all my greens, but 1 less marble. That's a 5. And now I have 1 less blue and 1 less marble. So this is 1 out of 9. Okay, so this is the probability if the first marble is an event, this is the probability that of what I'll get on the first marble. Now this probability is the probability of the second marble given that the first marble has already been chosen, okay? So this is where this relationship comes from. When that second event, the probability of that second event is impacted by the probability of the first event, okay? So as with a tree, to find all my ands, all I do is multiply down a branch, okay? Now, I've already done all these and I don't want to rewrite them, so I'm going to show you. Okay, so my event B is the first marble. So here I am pulling out the first marble, and these are all the probabilities of the first marble. Event A is the second marble. So this is me choosing my second marble, and these are all the probabilities of my second marble. Now, the probability of my second marble is going to be impacted by what marble I picked before, okay? So when I calculate all these ands, so red and red, 3/10 times 2/9, red and green, 3/10 times 5/9, okay? When I go through and calculate all these, what I'm really calculating is their and, which is the probability of an event times the probability of another event given that that first event occurred. Okay, so this is where this equation on our sheet is used, okay? So sometimes you'll have to calculate that, okay? And most of the time, I always see it in trees, okay? Now, just as a little aside, since we've got this lovely tree and I've written out all the calculations of all the ands down each branch, okay? Don't forget, all these branches represent every single possible combination of marbles when I pick 2 marbles from my bag. So all these probabilities should add up to be 1, and indeed they do. I left them all in fractions, okay? Okay, so now let's figure out our probabilities. Now we've got this lovely tree. We have every single probability written out. Let's answer some questions. What's the probability I'm going to get 2 blue marbles? Okay, well, all I have to find is the branch that's blue and blue. And I've already got the probability of blue and blue. So the probability of blue and blue equals 2/90. And we can keep it as a fraction, or you can write it as a decimal, okay? I'm telling you right now, if you have all fractions here, keep it as a fraction. You don't need to simplify your fractions. If you write all decimals here, then go ahead and write your decimals, okay? Like, I wouldn't have just put that because I don't know where that came from, you know? And you don't want something like that where you don't know where it came from, okay? All right, what's the probability of 1 green and 1 red marble? Okay, so 1 green and 1 red is right here. Whoops, 1 green and 1 red. But then 1 green and 1 red is also right here, okay? So we're basically going to need these 2 branches, okay? So we're going to need probability of red and green and probability of green and red. So we're going to do the probability of red and green, or the probability of green and red. Now the probability of red and green is 15/90. Whoops. Red and green is 15/90. And green and red is also 15/90. Okay, now it's one or the other. So when I have an or, I have to add them. So 15 and 15, that's 30/90. And that is 0.33. Okay? All right, last one. What's the probability I'm going to get the same color marble? Okay, so same color marble. I want red, red, green, green, or blue, blue. Okay? So I'm going to do the probability of red and red. Probability of green and green. And the probability of blue. Oh, you can't even see them right. And blue. And again, I have them all up there. Red, red is, sorry guys, red is 6/90. Green, green is 20/90. And blue, blue is 2/90. Okay, and again, it's basically a big or, this or that or this. So I'm going to add all these together, 26, 27, that equals 28/90, which is 0.311, okay? So again, these weren't conditional distribution. These were not conditional probabilities, but I wanted you to see where a conditional probability shows up in a tree. And it's always in a tree when there's without replacement or there's some sort of dependency, okay? Because these events are dependent. This probability of the second marble depends on what happens in the first marble, okay? All right, I think I have one more thing to show you. Yes, indeed. Okay, now let's do another question with a tree, and we're going to solve for a conditional. Okay, Shannon hits the snooze on her alarm on 60% of school days. If she does not hit the snooze, there's a 90% chance she makes it to class on time. However, if she hits the snooze, there's only a 70% chance she makes it to class on time. On a randomly chosen day, what's the probability that Shannon is late to class? All right, so if I think about this, she can be late to class after hitting the snooze, or not hitting the snooze. So this is a sequence of events. Okay, so a lot of times I'll use a tree when there's a sequence of events. Okay, and the probabilities are dependent, because if she doesn't hit the snooze, there's a 90% chance she makes it. If she hits the snooze, there's a 70% chance. So these events are also dependent. Okay, so let's talk about this. First thing she's going to do is either hit the snooze or not. Okay, Shannon hits the snooze on her alarm 60% of school days. So if that's 0.6, this has to be 0.4. Have to add up to be 1. If she does not hit the snooze, there is a 90% chance that she'll make it to class on time, which means there's a 10% chance she'll be late. Okay? Now, if she hits the snooze, there's only a 70% chance she makes it to class on time, which means there's a 30% chance she is late. Okay? On a randomly chosen day, what is the probability that Shannon is late to class? Well, this branch is late when she hits the snooze. This branch is late when she does not hit the snooze. So the probability of her being late is going to be the probability of her hitting the snooze and being late, plus or the probability of her not hitting the snooze and being late. So all I have to do is multiply down, because again, this is the probability of an event. This is the probability of a second event, given that the first event was that happened. So to find the and, I just have to multiply those two. So snooze and late would be 0.6 times 0.7, plus not snooze and late is 0.4 times 0.1. So this ends up being, oh, did I do 0.7? You know, I looked at that. As soon as I wrote it, I knew it was wrong. 0.6 and 0.3, because she's late, hits the snooze and is late, and then does not hit the snooze and is late. Okay, so that ends up being, what is that, 0.22, okay? So there's a 22% chance that she's gonna be late, okay? Whether she hits the snooze or not, it doesn't matter. She's gonna be late probably 22% of the time, okay? Now let's expand this. Suppose Shannon is late to class. That is a condition. She is late to class. What's the probability that she hits snooze? So that's the probability I want to find. So this is a conditional. What's the probability she hits snooze given she was late to class? Okay. Now for this isn't on a branch. I've got to go through my formula of the probability of snooze and late divided by the probability of being late. Well, conveniently, we just found the probability of being late. So that's 0.22 down there. And then for the probability of hitting the snooze and being late, we can find that from the tree again. So there's the probability, get rid of that other paper, of her hitting the snooze and being late. So I'm going to do 0.6 times 0.3. Okay, and then if I throw that in the calculator, I get 0.82. So there's a 0.82 or an 82% chance that if she's late, she hit the snooze. Okay, so this is just another example of how a tree can help you figure out a conditional probability. Okay, because on the AP test, they're just going to give you this scenario and ask you this question. So you've got to kind of work backwards, okay? So again, if you're given a table, the conditionals are pretty straightforward. But sometimes you're given a situation where it can't really be a table. It's a sequence of events. It's not two events occurring at the exact same time. So you've got to work through a tree. Okay. All right. Hopefully this was helpful, and I will see you guys for the next one.